Hello everyone, welcome to NLP session about word embeddings. So what you can see on the screen, this is a visualization, 3D visualization of word embedding model projection on 3D space, word embedding with 128 dimensions. Dimensionality technique is PCA applied to present this. And you may want to ask, what is this separate thing? So the data set I used to train these word embeddings was some medical publications, and this separate thing, you see there are data points with a kind of similar pattern, and interestingly that algorithm put it very close to each other. So this is how you can see how word embedding really works, right? That it places data points which has similar meaning very close to each other. And this is the rest of vocabulary where you have words and maybe some numbers, but other one, right? So let's see how to create this thing from your own data set. This data set I loaded from open source Hugging Face library datasets. We need to install it because this is not default one. These are import necessary libraries. I will use Tensorflow keras layers to train this word embedding model. What else we have to define? We need to define number of negative examples, negative words. For word embedding equal 10, we will use it later, and I mention it a little bit later in the code. And auto-tune, this is usual random seed 42. So we load data set. I picked, as mentioned earlier, PubMed data. I just needed some textual data set, and this was the first one which I picked randomly, and there was a text. This data set, it has, as usual, train, test, and validation parts. Train is a little bit big, 2.5 million rows, so I picked test 1, and this word embedding was trained on the test data set of this PubMed data. Right, so let's see what is inside this test data set. This simple function to calculate vocabulary, to build vocabulary out of our data set. So we can see that length of vocabulary is 42,883 tokens, words. What else we have? And this is simple analysis. Take a look at the data set. Now we need to, understand before building a word embedding model, we need to define some length of sequence we want to use to train our word embedding. Because as you know, all examples to train a model have to be the same length. And here I calculated mean and max value of text in the data set, and you can see mean is 136 and max is 930, so the difference is pretty big. I decided to go with 136. So it means that some long text like this one, which has length of 930 characters, it will be truncated, and some smaller one will be padded with zeros, empty. empty elements. Okay, let's store this value 136 in the variable sec length, and we will use it later. Get rid of this column we created, and then because I use Colab Google Drive, right? I need to mount it to do some manipulation with the files. So I mounted my drive, and to pass the data to a TensorFlow dataset, kind of create TensorFlow dataset out of my data, I will go through the text line dataset method, and here I need to pass a textual file and split all my sequences, right, all my text examples with the next line char. So this is what I did here, and in this cell I create training data in TensorFlow format. This filter is dedicated to get rid of empty rows. If we had somewhere in our data set just empty text example, so basically no text, so we don't want to put it into training data set, and this lambda function will do this. Kind of skip false when the length will be 0, it will return false, and that's it. Now we need to do some we will need to do some pre-processing. I will do the simple one just to get rid of punctuation, a standard one stored in this string punctuation. This is the default one. You may play with it, you may create your own sequence of characters you would like to remove. But here we just do this generic stuff and lowercase all our data. Now we need to create a vectorizer, because all text obviously has to be vectorized to be able to process, to train a model. We use layer text vectorization. This allows to use kind of mapping. This use our pre-processing function to standardize data. Max tokens, this is vocabulary length, which we calculated above. Input mode, integer values, because we want a sequence of integer representation for our text. And output sequence length, this is sec length 136, what we agreed above. Okay, now we need to create a vocabulary. So basically we use our vectorizer and adapt our train data in batches. And to save vocabulary, we can use get vocabulary functionality for vectorizer level layer. Right, so move on. Now we need to vectorize our training data. We need to vectorize it, right? So we map vectorizer in a batches to train data. After doing this, we want to obtain sequences of our text as a list of sequences which contains integer value, right? So this is what we do in this cell. Then we go to the next step. Let's take a look how does the sequences look like. So this is our vectorized representation, kind of integer representation of our sequence, and you can see here it is kind of a number which we saw in this separate cloud, small one, right? So some rows, they contains just this number, and that's it. The rest just padding. Next example, there is some text, you see, and it was short, so to have 136 elements, we padded the rest. Let's move on. Now we need to create a function which will kind of data generator where we create targets, context, and labels sets for future model training. Targets, these are our words itself, right? Basically, this is a word. Context, this is a context around this target word within a window. This is a window. Window, for example, we will pass 5. It means we will take a look at the 5 words before target word and after target word. This is our window. And assigned label. Okay, we will use skipgram model. There are two basically models for word embeddings. Main one, these are CBOW and skipgrams, right? CBOW, this is continuous bag of words, and skipgrams, this is what we use, what we want to use now. This approach. Okay, so in Tensorflow they also have this functionality to generate skipgrams. Let's use it, and what it will do for us, it will generate positive words. Positive, it means it will give us representation of the context. Also, we need create a negative candidates. Negative, these are words which are not close to our target word. So these are basically false context for our target word. And to create this, this set of negative words, we use a log uniform candidate sampler. So basically we randomly pick out of our text words which are out of the context our target word. And here we use this num negative, which we define just at the very beginning, which we defined as 10. Here. So this is where we use this variable. Okay. So we generate also negative sampling candidates. And what we do next? Next, we create a context concatenating our positive context and negative, and assign a label. So this is data generator to create all these sets. Right, so this is where we do. This cell will take a time to run. You see, it took around 15 minutes to run for me. These 32K examples. Window I picked 5. This is pretty common. You may play with it. You may have window larger or smaller. Vocabulary learn and negative we discussed, and sequences. This our list of this integer representation, right? A kind of arrays. Okay, so we have our data created, generated. Now we need to turn them into NP arrays, NumPy arrays, to be able to use by TensorFlow in this step, next step. So here we create a TensorFlow dataset where we put together target and context and assign a label for this pair. Now we define a class W2VEC to train our model, to create layers and general stuff, right? So on initialization step, we will define target embedding. We need two embeddings, right? Target embedding, like our words, and context embedding. So both these are embedding layers with such parameters. Target embedding, we assign a name because we will use it later. We will need it later. Call method is to basically to do the job of producing dot product from our word embedding targets, right, and context embedding. So here we do the dot product basically to make a prediction and compute loss function. This is where we run everything, we call everything. Embedding dimensionality 128, as you can see here. You may also play with number of dimensions. We pass our vocabulary length, embedding dimensionality, to initialize word embedding as an object. Then we in compile we pass optimizer, define optimizer, Adam optimizer, loss function is a big standard one for categorical cross entropy, and metrics accuracy, because we have TF keras model as a basis. Also we want to have statistics, log training statistics. So we need this, and this where we train the model, basically method fit. We'll start training. I run it for 20 epochs, and you can see here callbacks uses this TensorBoard callback, so we will be able to see statistics. And you see, interestingly, we can just observe how it learns with every single epoch. The accuracy is just improving, and from 17% we reach 80% accuracy, right? Loss 5.6%. So you may run it in more epochs, or if you run it again, it will improve accuracy. This is how it learns. Now we can basically, because we trained the model and it learned weights, and we basically need just weights out of this model. To get embeddings, kind of weights from the model, we call getLayer method, and we pass this name W2VEC embedding, which we defined here, because we want these specific weights. Get weights, and for vocabulary we have our vocabulary out of vectorizer. Actually, I stored it above in different variable, I think. Yeah, I stored it here, so this is the same thing. Vocab vectorizer. Now you need just to save vectors and words vocabulary. These usually are two separate files, TSV, tabular one. So you just save them, and basically that's it. This is how you download them locally. You open Tensorflow Embedding projector and upload your file. This was my upload. I uploaded vectors and metadata. This our vocabulary, and it will map. Actually, you even can they can show you a projection without even metadata. It will still be presented, but it will be ugly, right? You will not know. But here you can just, for example, if you pass virus, let's try virus, and you see the closest one, kind of poliovirus, papillomavirus, rotavirus. So all these words are the closest one to our target. You see, this is where they are located. Basically that's it. If you have any questions or suggestions, please leave a comment below the video. Give me a thumbs up, subscribe on the channel, and see you next time. Bye!